Good morning. How is everyone?
Good.
Great.
Great. Okay, I want to go back to our the uncountability of the real numbers for just a little while, and then we'll get into proofs today. Okay, remember we showed that the real numbers are not countable with the proof by contradiction. In other words, we assumed that they were countable, and then showed that we run into a contradiction with that. So assuming that they are countable, the way we characterize that is to say, well, if they're countable, then that means we can make a list of them. And remember, we said also we showed that we really only need to work with the real numbers between 0 and 1. And so we said, okay, so if you do assume there's a list and they look something like this, etc. What we showed was if there was such a list, then we could define a real number that wasn't in the list. That was a contradiction. Okay, well, what does it mean for the number to not be in the list? It means that this number has to be different from each and every number that's in that list. And that means that if it at least needs to be different in one position. And what we chose was like for this is the number that's not there. Let's call it X. Okay, and so for the first position in this, what we decided is, okay, we will make that different from the first position of the first number, which would be this. So to make it different, that was 0, we make this one 1. Now for the second position in the number we're creating, we make it different from the second number in the list. And where we make it different is at the second position of the second number in the list. So that was a 1. So this will be a 0. And for the third one, we'll make it different than the third position in the third number in the list. So it'd be like that. So using this, I'm constructing a number that is different from any number in the list, right? Because I've made it different in at least one position from the first number of the list, from the second number and the third number, etc. Any questions on that? Okay, there was a question asked about this. This is the diagonal. In picking these places where to make it different, are there other ways you could do it? Yes, there are. But I haven't actually seen anybody do this, but let's say this is our number, and and we want to make this number different from every number in the list. Okay, well, let's say I pick this location, and I'm just going to call it 1. And say I pick some other location, we'll just call this 2. And say down here, I pick 3. And I have some location that I picked for each natural number. Okay, now for this number, what I want to put down, this is the second position in the number, right? I want to make it different than the second position in the first number in the list. These are the numbers in the list. And for this one, this is, oh, I guess I've got to put in my other marks here. For this one, I want it to be 1, 2, 3, 4, 5. This one I want to be different than the fifth position in the second number in the list. Okay, this is doing the same thing as we did up here. It's guaranteeing that you pick any number in the list. There's a position on this number we're constructing that's different Okay, and notice if you do it this way, we actually don't even care what's in these locations, right? It could be anything. So if we did this construction, we're actually creating not just one number that's not in the list, we're creating many numbers that's not in the list. So definitely the assumption that you could put all of the real numbers into a list, in other words, that they're countable, leads to a contradiction. Any questions on that? Okay, one more thing in sets, and then we'll get back to this countability argument in a different context. I don't think that we talked about the power set before of a set. The power set is a set of all subsets. And there are different ways of notation for this. Like the script PS could be one notation for power set. Another one is to take the number 2 and put an exponent on it that's the set S. This is just means exactly the same thing as this, the set of all subsets of S. Example, let's let S be 1, 2, 3. Okay, then the power set of S is going to be a set that contains sets, and those sets are the subsets of S. Okay, the empty set is a subset of every set, so it's definitely in here. Okay, and then there are sets of S that only have one element in them. Those are called singletons. And then there are sets that are made up of 2 elements of the things that are in S.
Question?
Sure.
In your example, is that 2 to the power of S?
Yeah.
Okay, cool.
Yeah. Okay, so we got what? I've got one more here I got to do, right? So we did 1, 3. This is 2, 3. How about, did I get 1, 2? Yeah, no, I don't. Okay. And the whole set. Okay, so how many things are in here? Hopefully there are 8. Okay, notice the cardinality. That will, in general, be true. Okay, remember we use this symbol for an alphabet. And let's say that we're going to do this typical alphabet that we have here, 0 and 1. Then we can talk about sigma star. And what is that? That's all strings over sigma. So this, in this case, this would be all binary numbers, right? Okay, well, a set of strings is called a language. And so given an alphabet, there could be many different languages that are built up on that. And so it could be any set of strings that's in sigma star. So that corresponds to, if we're talking about the set of all languages, that's what it is. Now, is that countable? Sigma star is countable, right? The set of all strings over some alphabet. But what about this set of all subsets of sigma star? Okay, well, it's not countable. And here's a proof of it, and it's going to be just very similar to the real numbers. Okay, so again, well, first I'm going to show a way of representing subsets, let's say, of sigma star. So one string is the empty string, and there's strings that only have one symbol in them. I think you saw this before when we were showing that sigma star is countable, right? And then we've got the two things. I'm thinking of reading this from this way. Strings of size 2. And then strings of size 3, etc. Now I can represent a subset of this by just marking the strings that are in the subset, right? Like say it's got this in it, and it's got this one in it, and it's got this one. Doesn't have this one, doesn't have this one, doesn't have this one. So in other words, it's a string of ones and zeros, where 0 means that string's not in my set, 1 means that string is in my set. I can represent every subset of sigma star with such a string of ones and zeros. So doesn't that look like a real number between 0 and 1? No, we have the same argument here. If we assumed, remember each line here is going to represent a subset of sigma star. If we assume that the subsets of sigma star are countable, then it would be possible to write a list of them. And then argument by contradiction, same as we did with the real numbers, would be if there was such a list, we can define a subset that's not in the list. So the list couldn't have been all of the subsets in sigma star. And again, we would do it the same way we did before. The diagonalization argument. So this subset that's not in the list then is going to be 1, 0, 0, etc. Questions on that? Okay, this this actually leads to something else that's rather dramatic, I think. And that is, if you're talking about some kind of model, some kind of machine that can recognize strings, in other words, recognize words, and you could use it to define a language, like say all of the words that this machine accepts is the language that I'm talking about. Then if those machines can be totally defined with a finite number of ones and zeros, the machines are countable, right? But all possible languages is not countable. So what does that mean? That means that we couldn't use such a model to represent every possible language there could be. We'll return to that later. A few weeks anyway. Still, any questions? Then let's go on to proofs. So what is a proof? Some people think that a proof can get to some kind of, especially if we use logic, that we can get to some kind of absolute truth. I don't think so. In fact, one of the best definitions that I ever heard for a proof was something that a fairly famous mathematician named John Milner told the student when the student, he was at Princeton at the time, when the student asked, what is a proof? Milner said, it's an argument that will convince another mathematician. And so what does that mean? What does that imply? That for one thing, I think that a proof effectiveness is going to depend on the audience, and its appropriateness is going to depend on the audience. So if you're going to convince another mathematician of something, then you better be working with a set of things that make sense to that mathematician, both the type of logic you use and the types of definitions that you use. There's a vocabulary that goes along with proofs. This is certainly nothing for you to memorize. But just in case you run into these words and wonder what the heck do they mean, it's worth going over it once. A big thing, it's a small thing in this list is definitions. This is a super important thing because everything in your proof is going to depend on what the things in the proof mean. So if you're asked to come up with a proof for something, be sure that you know what the definitions of the items are that are being talked about. Okay, things are called theorems, and we want to prove those. We want to prove propositions. We want to prove lemmas, and things called corollaries. All of these things is just some statement to be proved. And their different names is really just some kind of subjective evaluation about how important they are. Like a real important thing, well, we'll call that statement a theorem. Something that's not so important, we'll call a lemma. Something that's in between, we'll call that a proposition. But all these things, it's just some statement to be proved. And corollary is just something that's easy to prove after you've gone through the proof for a theorem. Okay, then we've got some other things which, when we're doing a proof, we can make use of. And these are statements that we will assume are true. And those can be axioms or postulates. Any questions on that? Okay, the other big thing is conjecture. This is something that we think is probably true, but we don't have a proof for it yet. So what are proofs good for? Any ideas? You guys are so quiet today. I think that what proofs are needed for is a way that we can avoid faulty reasoning. It's a way for us to feel confident about the thing that was a conjecture is true given the definitions that we're working with and the logic that we're using.
Hey, Professor.
Yeah.
Would you have an example of some of the different types of like the proofs in the previous slide? Because sometimes I have a hard time differentiating them when I encounter them in textbooks, like axioms and postulates.
Well, an axiom is not a proof. So I'm not. We're going to go through a whole series of different kinds of proofs.
Yeah.
Yeah.
Okay.
Yeah. Okay, but back to what's a proof good for? And I think it's, again, I would say it's good for avoiding believing conjectures that may not be true. So let's take a look at some famous ones. In the 17th century, Fermat had an interesting conjecture that, and it's numbers that have the special form, say 2 to the power 2 to the n plus 1 are primes, that all of these numbers are prime. And if we take a look here, well, let's try different values of n. So say n is 0, then this thing is 3. If n is 1, this thing's 5. If n is 2, it's 17. If n is 3, it's 257. And if it's 4, you must have had fun computing this way back there in the 17th century. Okay, and it's true for all of those. So have we proven the conjecture? No, we just gave examples of where it's true. In the 18th century, this is 100 years later, right? Euler showed that 2 to the 2 to the 5th, in other words, the next number here, plus 1.
You're a doctor.
Pardon?
I'm a doctor.
Pardon? Okay, so in the 18th century, Euler showed that this, in other words, the next Fermat number.
He gave a really funny expression.
Andreas, you're unmuted.
Okay. So Euler showed that this number is equal to which is not a big deal because you just take the time to work that out, right? But what was the big deal is this thing a prime? Remember, it's not easy to prove that numbers are prime. To find that it's not easy to factor numbers if we talk about the general case. What Euler showed was that this is equal to 641 times 6700 417. So here, this is not prime, right? So this is a conjecture that that worked out to not be true. Another example is, let's say, numbers of this form, 991 n squared plus 1. And the conjecture is that these things are never perfect squares. Okay, with those, you can try ands all the way up to something like this. The very first time you'll run into one that is a perfect square would be here, let's say.
So basically,
And this goes on and on and on for at least 10 more places. And so there are a whole bunch of examples of this thing being true, but there's at least this one counterexample. Right, so in general, we'll find with proof that it doesn't matter how many examples you have of something being true, that does not prove it. But to show that something is not true, just one example is sufficient. All right, so you can unmute yourselves again. So I'm checking to see if you got any questions on that.
Professor?
Yeah.
So I guess in terms of the vocab, what's the difference between like an axiom and a postulate, which you assume to be true, versus a conjecture, which is probably true but no proof?
Well, the conjecture is not probably true.
Oh.
Okay, and the difference between an axiom and a postulate, oh, my speculation would be that axioms are more fundamental. You usually have fewer of them. If we go back to plane geometry, you'll find out that the number of axioms is quite small. And then postulates, there may be, I don't know, probably maybe 20 or so. So there really isn't, strictly speaking, there really isn't some difference. It's just things that we're assuming to be true. And then we're going to build proofs based on those. Are there any other questions? Let's see, the main thing that I'd really like to get out of this is that we are very suspicious of something being true just because it's true for a lot of cases, and realize that if we want to get to is that thing true for all cases, that we need to do a proof. We can't just do it by examples of where it's true.
So will we be proving some formula about the primes next?
Yeah, and in the examples I have, there's one thing we'll prove is that is that every number is divisible by a prime.
Okay, thank you.
Sure.
Professor,
Yeah.
I was wondering whether you could go back for a second to the notes about with the vocabulary.
Oh, wow. Sure. Remember, don't memorize this thing. This is just, you run into these words, I know, and you may think there's something mysterious about them, but there isn't. You definitely don't need to memorize them. So what's your question?
Oh, I just wanted to have it there, so I've screenshotted it.
This will be in the notes I release anyway.
Thank you.
Okay, so I talked about what a proof isn't. So let's talk about the some ways of doing proofs. Okay, very popular one. We'll run into this and want to use it in a lot of places. Is the idea of induction. And I'd say at the base, what this is really related to is say you have some set of natural numbers, and we know that this set contains 1. If we, in addition to that, we know that any number, if some number is in the set, that its successor is also in the set. Successor means the next number. No, the successor of 2 is 3, successor of 9 is 10, etc. So if we have a set of natural numbers and we know that 1's in the set, and that if n is in the set, then n plus 1 is in the set, then what can we conclude from that? The set contains all of the natural numbers. And that's all induction is. Okay, so but in this case, what we with induction, what we're the way we're going to use this is we're talking about some statement and whether or not that statement's true. So we've got some statement that can be parameterized by a number n, let's say. And if we can show that the statement with n1 is true, and if it's true for n, that it's true for n plus 1, then all of these numbers is all natural numbers. So then we can conclude for all n, this natural number, that Sn is true. Okay, so the way that we do an inductive proof is to show that that is true for 1, and this could also be some finite number, like that is true for 1 is true for 2, etc. And then if we show that if it's true for any number, that it's true for the successor, the statement, then we take that as proof that it's true for all of the natural numbers. Okay, maybe another thing to give you the feeling that this is a reasonable thing is notice that basically with this little format here, what we've done is shown a way that if you take any number and say, okay, I want to prove that Sn is true for that particular number, then you could construct a proof where we show it's true for 1, and we show that this implies 2, and that implies 3, and that implies until we get up to our number. So if we've shown these steps in doing an inductive proof for something, it's certainly true that given any number, we could use that scheme to prove it for that number. Any questions on that? Okay, so let's look at an example, and what I want to look at are the sum of the first n odd numbers. Okay, well, let's take a look at what these things are. It's fairly easy for us to establish for ourselves that that's 1, right? And so we'll find out that that's 1, that's 4, this one's 9. Oh, let's do one more. Well, 9 and 7, 16. Well, we're already beginning to get an idea here, right? In fact, this is a way to come up with conjectures, is to just look at the numbers in the set that you're concerned about, and get some idea of what's going on. So I think for all of us, we can see right away that a good conjecture is these. Let's see what this is: 1 squared. This is 2 squared. This is 3 squared. 4 squared. Wow. We'll say that Sn then is equal to n squared. Okay, but are these examples a good enough thing to say, here's our proof? Anybody think that's a proof?
No.
No.
Ah, good. Okay, so let's use induction. Okay, so our basis is 1. What we have then is that S1 is equal to 1, and 1 is 1 squared, so it's true. Then what we want to do is to say, if it's true for some particular n, that it must be true for n plus 1. So what are we saying there? We're saying assume that it's true for n, and then prove that it's true for n plus 1. So I want to assume and from this assumption show that it's true for n plus 1, which would be Sn plus 1 is equal to n plus 1 squared. Okay, so S for n plus 1, and now this is just going to be algebra. It's certainly going to be whatever it was for n, plus the plus the next odd number. Okay, and now here's where our assumption is going to come in. This, as I said, is just algebra. But now we're going to make use of our assumption to put in the value for Sn. This assumption is, the vocabulary for that is, it's called an inductive hypothesis. And so we'll use it here. And that's saying that Sn is n squared, there it is, plus And of course, that's n squared. In algebra again, of course. So if you were showing your steps, going from this step to this step, you could do this little deal and say that's from the inductive hypothesis.
Is there a reason why you did 2 times m plus 1 minus 1 instead of plus 1 outside the parentheses?
Here,
Yeah, at the very right side. Is there a reason why you did minus 1 instead of plus 1?
okay, well, if you do plus 1, it's not going to be the next one, is it?
The math wouldn't work out, but the definition of an odd number is 2 times some number plus 1 or minus 1.
Right. And in this case, the next one would actually be this, not plus 1.
Okay.
If you work that out. That's the n plus 1th odd number.
N plus 1 odd number. Okay.
And this was the nth one, right?
Oh, yes, I see. Okay. Thank you.
Yeah. Okay, any other questions? So, okay, this kind of inductive argument that goes from where in your inductive step of the argument, you show that if it's true for n plus, if it's true for n, it's true for n plus 1. You could also frame that as if it's true for n minus 1, it's true for n, right? This is called weak induction. And that doesn't mean that it's weak. It's just the name that it's given. And there's another thing that's called strong induction in contrast with this. So if the weak induction is, in the inductive step, you prove that if it's true for n minus 1, it's true for n. With strong induction, what you do is you prove that if it was true for all numbers less than n, it's true for n. That doesn't say that you have to prove that it's true for all numbers less than n. It's just saying if you assumed that it was true for all numbers less than n, can you then show that it's true for n? Okay, sometimes that's a lot easier to do than just doing the n minus 1 case implies the nth case. And I can give you an example of that. Okay, what I want to prove is that any natural number let's say greater than 1, it's divisible by a prime. Okay, so again, we need a base case. And so let's see, this is we're using this as n, then our case is this statement. Okay, well the statement is saying that 2 is divisible by a prime. Yes, it is a prime, right? Okay, now then let's look at any n that's bigger than 1. Then it's either a prime or it isn't, right? If it is a prime, then it's divisible by a prime, obviously. Okay, if it's not a prime, then what? Well, saying that it's not a prime is saying that it's the that it must be divisible by something other than itself in 1, right? So let's say so it must be, let's say d times by some other number. Both of these numbers, neither one of them is a well, we don't know that. Okay, so anyway, so n's not a prime, then it must be factorable into 2 numbers, where neither one of them is 1, right?
I have a question about the previous statement.
Yeah,
You said for any m greater than 1,
yeah,
and then if it's a prime, then it's divisible by a prime.
yeah,
But
itself.
okay, so we're counting itself here. Okay.
Yeah,
All right.
yeah,
Thank you.
all numbers are divisible by themselves.
Yeah.
Yeah.
Thank you.
And so if they happen to be a prime, then they're divisible by a prime. Okay, so if it's not a prime, then it's two other numbers. Okay, we also know that the d is less than n, right? G is less than n too, but we only need to work with 1 here. It's less than n. Okay, well notice d is not necessarily, n minus 1, right? And so if all we had to work with was weak induction, we'd be stuck here because we don't know that it's true for n minus 1. I mean, we don't have an n minus 1 here, but we do have something that's less than n. And the inductive step with strong induction is if we can show that making the assumption that it's true for everything less than n works, that's good. Okay, so by our inductive hypothesis, d is divisible by a prime. And let's say p. Okay, but if n is d times g, then n must be divisible by p. Is divisible by p So n is divisible by p. Okay, so here was a case where you couldn't do this by showing that if it was true for n minus 1, that it'd be true for n, but we could do it by showing if it was true for something less than n, that it would be true for n. Questions on that?
Yeah, on the inductive hypothesis part,
Yeah.
are we assuming that, or my question is, how do we know that D is divisible by a prime? That seems like something that we just assumed, but we didn't really like show where it came from.
Indeed, we did just assume it. And,
Oh,
and what
okay.
and what we're trying to do is to show if we make that assumption
Mhm.
that this is true for all numbers less than n. If we make that assumption and can show that then it must be true for n, then that's our inductive proof.
Okay, I mean that makes sense, but to me this doesn't feel like a very like valid or solid proof because we didn't really show what happened to D other than just assume what we need it to be in order for us to complete the proof.
To make it feel more comfortable, remember that we showed back for the case 2.
Yeah.
Okay, so then given that, using this reasoning, that would show that it must be true for 3, for 4, etc. In other words,
Okay.
if you can assume that it's true for numbers smaller and prove that it's true for n, that's just one piece of an inductive proof, right? The
Yeah.
other thing is you have to show for one of those smaller numbers way back there that it is true. Then that whole chain takes effect.
Okay.
Yeah, so you're right to have that uneasy feeling about, well, we really didn't show that D was divisible by a prime, but but what that required was that we went back far enough in the chain to where we actually did show something was a prime, and in this case it was 2.
Okay. So in this chain, then you'd say 2 is divisible by a prime, which is itself. 3 is a prime divisible by itself, and then 4 is divisible by 2, and then 5
Yeah,
is divisible by itself, and so on. And then that
right,
chain gets you all the way to D, which is what we need.
right.
Okay.
Except you don't have to show all of those little steps if you just show that if you assume that it's
Mhm.
true for everything less than n, that it must be true for n.
Okay. All right. Thank you.
Yeah. Okay, and there's some people think that actually the only induction that you need to use a strong induction, just use it every place, and that includes the case where you just assume that it's true for n minus 1, right? Okay, then sometimes a proof could just be a very direct thing. Let's say like odd numbers are the difference of 2 squares. Okay, so odd numbers like this, right? It's an I plus 1, where I, u Let's see, if we want to get them, then it's going to have to be 0, right? Okay, so I want to show that that it's a difference of 2 squares. Okay, here's some algebra. I'm going to take this thing and add to it I squared. But if I added to it I squared, then I want to subtract I squared. Okay, so this is just algebra. Square, square. Any questions on that one?
Sorry, can you show again how you got to the middle line?
This one?
Yes.
Oh, I added I squared and subtracted I squared, so it's still the same thing, right?
Okay. Yes.
Yeah. Another thing with this is if you examine this little construction, like say here I've got 1, and then here I've got 1, 2, 3. Okay, well notice this is 1 squared. This one's 2 squared, right? And this
Yeah.
one is 3 squared. Okay, so and if we look at if we go around these borders, these are the odd numbers. There's 1, 3, 5. So you can see if I take 9 squared and subtract, that means if I take 3 squared and subtract 2 squared, I've got an odd number here, right?
Yes.
Yeah, and
Okay. That's cool. Thank you.
yeah, I think this is more fun than the algebraic magic.
Sorry, could you identify which of those is 2's and z's? I'm having difficulty reading it.
Which ones?
I'm having difficulty telling the 2's and the z's apart.
These?
I think there's a variable z in there, isn't there?
That's what I use for I. Is that what you're talking about?
Oh, okay. It's an I. Okay, thank you.
But actually, it doesn't matter. It doesn't matter what it is. It could be a Joe, right?
Yeah, I was just trying to determine variables from numbers and was getting confused.
Yeah. Yeah. So I
Thank you.
make I's like that and J's like that. Okay. Okay. Now another technique is to when you're trying to prove that something implies something else. Like if you want to show that P implies Q, that may be kind of difficult to do. But it might be easier to show that not Q implies not P. Okay, you can use truth tables to show that these two things are equivalent. This is called the contrapositive of this. So there are cases indeed where it could be difficult or messy to do this, but easy to do this. And let's take a case. say p squared even implies p is even. Okay, that, if you try to do that directly, I think you'll find that's kind of messy. Like if you use some general expression for p squared, getting from that to the p must be even is messy. You can do it with a cases type argument, but that's a little bit of a mess. And it's so simple if we just use the contrapositive. So what we do here is we'd say p not even implies p squared not even. So what we got is p is, let's say 2n plus 1. It's an odd number for some n. Then, so this is not even, right? Then p squared is going to be 4n squared plus 4n plus 1, which is 2 times 2n squared plus 2n plus 1. So this is 2 times something plus 1. So we were able to show that p not even implies that p squared is not even in 3 lines, right? Any questions on that? Okay, and I think it'd be worth the exercise for you to use truth tables and convince yourself that these two things are equivalent. Next time, we're going to make use of knowing this. The p squared being even implies that p is even, in a fairly classical proof that the square root of 2 is not a rational number. Okay, any questions? Okay, and see you on Wednesday.
Thank you.
Thank you.
Thank
Thank
you.
you.
Thank you.
The professor.